less.
Okay, yes, especially. Okay, so um, welcome everybody to another session of the CCPBioSim Industry Talk series. And it's called Industry Talk because we like to get the opportunity to hear about what's happening in industry. But of course, that does not mean that we don't like people from academia. So today we are fortunate to have a great speaker from academia, David Hardy. And David is a pretty hardcore and very experienced mathematician and programmer. He's calling today from the US, so we are very grateful that he's really taking the time to do that early in his day. So David received a BS in Math and Computer Science from Truman State University, where his studies included advanced work in algebraic coding theory and also some original research in graph theory. And then, so we definitely have, a little bit of a mathematician here, which is great. Then David followed by an MS in computer science from Missouri University's University of Science and Technology, where he did some original research and thesis work developing multiple time-step symplectic integration. I just learned this word today, and apparently it's a useful word to know. Then David received his PhD in computer science from the University of Illinois at Urbana-Champaign in 2006 under the supervision of Professor Robert Skeel. And then David went on to postdoc, still I think at Urbana-Champaign with Professor Klaus Schulten, will probably be very well known to this audience. And then then David contributed to the development of NAMD and VMD softwares, which are, of course, very well-known programs. And then David became a member of staff at Illinois University, at Urbana-Champaign, and where he continued to work on various things, including he's now the lead developer for the program NAMD, and David is very proud that he also contributed to the groundbreaking SARS-CoV-2 simulation research effort at UCSD with Professor Romy Amaro. So after this introduction, so David's title today is Accelerating Discovery with NAMD3 Simulation, a New High-Speed Computational Microscope. So the floor is yours, David.
Well, thank you very much. It's a very kind introduction, and I hope I live up to everything. So, I don't know. This talk doesn't have much mathematics in it at all. This is all about our work over the past few years in NAMD. And really what we're trying to do with NAMD is take advantage, as best as we possibly can of GPU computing and make NAMD run really well, as efficiently, as effectively as possible on GPU accelerated platforms. And so if you're not already familiar with NAMD, it's a scalable molecular dynamics program. And it's really well known for its ability to run in parallel, scaling to tens of thousands of CPU cores and thousands of GPUs. And the development of NAMD dates back to the mid-90s under the direction of Klaus Schulten. It is written in C++, and it uses CUDA for GPU acceleration on NVIDIA GPUs. And more recently, we use Hipify to be able to have a HIP translation to run on AMD GPUs And we are also now working on a SYCL port of our CUDA kernels. SYCL is SYCL. And so that's a new GPU device programming language that will allow us to run on Intel GPUs. And so, there's been a lot of activity now with not only trying to continue to support NVIDIA GPUs really well, but now also try to get good support too for AMD GPUs and finally Intel GPUs. Um, it uses Charm++ parallel objects to do its multi-node parallelism. And Charm++ is also developed here at the University of Illinois. And really the two uh, these two pieces of software sort of grew up together. NAMD became the big production application that was using the parallel frameworks that were being developed in Charm++. And so that the two have a very synergistic relationship that dates back to the late 90s. NAMD is a full-featured MD application with many advanced features. We have some really good free energy methods. We have a lot of enhanced sampling methods. We have a built-in collective variables module called Culvars, and it's highly customizable with user scripting that is traditionally done in TCL, but we can actually build NAMD in ways that will allow Python, some level of Python scripting too. And so when we think of parallel scaling of an molecular dynamics simulation, we can think of strong scaling, where we take a single simulation that's scaled across multiple computational resources. And so when we're trying to map this to hardware, if we're looking at something that's a CPU-based resource, this might mean like 2 to 10,000 atoms per core. Uh, and if we're looking at a GPU-based resource, this might be 20,000 to 100,000 atoms per device. And so, that just kind of gives you an idea of, how you might want to map the system that you're simulating to whatever your available hardware resources are. And like I said, strong scaling is the idea of you've got a fixed problem size, and then you're just trying to scale it up to use whatever your resources are. And then weak scaling, on the other hand, is the idea of having a multi-copy or replica exchange simulation in which the total number of simulations scale with the computational resources. And so to take advantage of this, you might want to determine your most efficient use of your resources for your simulation. So this might mean one copy per node or one copy per GPU device. And then you scale your total number of copies accordingly to, whatever it makes sense for your investigation or the resources that you want to use. So NAMD has a nice variety of force field and modeling support. Um, we have very good charm force field support, and not to be confused with Charm++ that I was talking about earlier, which is a parallel programming framework. But Charm is the force field development that takes place originally out of Harvard. And so NAMD has grown up supporting Charm, and over the years we've improved our support. In fact, for NAMD 3 now, we've got dramatic improvements to our support for Amber, file, and force field. And also we have some support for GROMACS as well. We along with the traditional, non-polar force field models, we also have support for the Drude polarizable force field. Um, most people use the tip 3P 3-point water model, but we also have support for the 4-point water models, tip 4P and OPC, and the 5-point Drude water model, SWM4 in DP. I don't even know what that acronym all stands for. But anyway, that's the water model if you're running a Drude polarizable force field. Um, we have some limited support for Martini, and but we don't really have up-to-date support for that. Um, our main file support are, using PDB files, PSF files, the force field files that you might be reading, say, from Charm, and then NAMD produces DCD trajectory files and can also uh, write out these NAMD binary restart files as well. So we have a large variety of what you might call standard features for equilibrium simulation that allow us to run at constant energy, uh, use temperature controls. So for, and this includes Langevin thermostat and more recently stochastic velocity rescaling, or if you want to do something pretty simple, but, it doesn't really reflect the canonical ensemble anymore, the Berenson heat bath. Um, we also have pressure control methods, and Langevin piston is really the most used method for that with Langevin thermostat. Um, and we support periodic boundary conditions with long-range electrostatics being calculated using particle mesh AWOLD. But we also have some support for doing non-periodic boundaries with spherical or cylindrical boundary conditions. And we can make use of a method called multi-level summation method for long-range electrostatics for these cases. Um, we have rigid bond constraints for hydrogen. That's commonly used. Multiple time stepping. And we also have ways of running that conserve momentum while still conserving energy. So that's the zero momentum uh, option in the code. We also have some energy minimization methods as well. And so these are probably the four things here that are maybe less common or sort of distinctive NAMD things. And most commonly used out of this is the pressure control, the Langevin piston pressure control, and the multiple time stepping. Uh, we also have a number of advanced features for non-equilibrium simulation. So we have a number of enhanced sampling methods where the user is applying external forces to maybe try and accelerate or drive a simulation of their system to examine uh, maybe some sort of conformational change in the system. Um, so we have a number of methods that people can use: harmonic restraints, fixed atoms, external electric field, steered MD, interactive MD, grid forces. Um, we have ways to boost or modify the interaction potentials to flatten out the energy landscape. And so these methods include accelerated MD and Gaussian accelerated MD, the solute scaling with REST2, and of course, replica exchange molecular dynamics. We build NAMD and distribute NAMD with this collective variables module called colvars. It's a very flexible module. It allows a number of force biasing techniques or analysis techniques. We have a rich a variety of alchemical free energy methods that include a number of ways to do free energy perturbation and also thermodynamic integration. Uh, we have constant pH simulation available. Um, we've got hybrid QMMM simulation available. And of course, we have this very flexible scripting interface that in primarily in TCL that can be accessed through the NAMD configuration file. And so we have some exciting features now in NAMD 3. Um, the latest version of NAMD 3 is Beta 6. And if you've been using earlier versions, I highly recommend that you upgrade immediately to Beta 6 because we've fixed some important bugs. And so we're very close to having our final release now. Um, the big innovation in NAMD 3 is a new GPU resonant mode for very fast dynamics. So this achieves a 2x or more speed up on single GPU versus our traditional GPU offload simulation. And yeah, we have efficient single node multi-GPU scaling for architectures with tightly coupled GPUs like the NVIDIA DGX architecture. And GPU resident mode is supported now both on NVIDIA and AMD GPUs, at least the AMD GPUs that are compatible with HIP. We now also have GPU support for our alchemical free energy methods, FEP and TI. Our GPU resident mode provides some advanced feature support now too. This includes harmonic restraints, external electric field, steered MD, REST2, and replica exchange MD. We have advanced foresight water models now supported, so TIP4P and OPC. We now, with Beta 6, we have Colvars and TCL forces both supported that enable the user to define external forces. And a couple of features that are only available for GPU resident mode now are the Monte Carlo barostat and group position restraints. I'm going to tell you a little bit more about those in upcoming slides. We also have a new CPU vectorization mode that supports AVX512 instructions. This can accelerate NAMD on CPU-based platforms that are using Intel Xeon CPUs or the new AMD Zen 4 CPUs. So NAMD has our NAMD development has worked really hard to support the all of the mainstream hardware choices that are available. And so we have support or have had support. We haven't really taken support away. It's just some of the platforms now are, gradually being, superseded by other platforms. But we've got a lot of good CPU-based support on x86, the new ARM GPU CPUs, Power and Knights Landing CPUs. And like I said, we have this AVX512 accelerated mode that we can use on x86. We have a lot of GPU accelerated support as well. And we offer builds for CUDA for NVIDIA, and we don't currently offer HIP builds on our website, but it's not difficult to download the code and build yourself for that. We When we're doing GPU acceleration, we have two ways of doing this. We've got our classic GPU offload mode where the force calculation is offloaded to the GPU device, but all of the numerical integration and rigid bond constraints and stuff are still performed on the CPU. And then, of course, this new GPU resident mode that I was just telling you about on the previous page, where almost all of the calculation is performed on the GPU device, and the atom data resides on the device between time steps. That's what makes it so fast. And so this is available now. The GPU resident mode is available now in our multi-core CUDA and Netlurt's SMP CUDA builds. Multi-core CUDA would be for just a single process, single simulation, and the Netlurt's SMP build would be what you would use for using this with replica exchange type methodologies or multi-copy methodologies, in which you're running each of your simulations as a single process on, one GPU up to maybe all the GPUs in a node. And you enable this with the config file keyword CUDA SOA integrate on. And so that's how you run now in this new GPU resident mode. We also have advanced feature support, but it's somewhat limited for the accelerated modes. And, that's because in order to run GPU resident, you actually have to make, and to run effectively GPU resident, you have to make the feature itself and all the extra calculation that you're doing, you have to port that to the GPU. And so we've been able to do that for some of our features, but we have not been able had the opportunity to do that for all of our features yet. And so you can just think of this as, you you can get, good acceleration out of NAMD, but, then you have maybe less features, advanced features available to you. So let's just back up a second and talk a little bit about what we're doing really with molecular dynamics simulation. So at its heart, we're integrating Newton's equations of motion. And so this is a system of ODEs where the force field that we're calculating is really it's the derivative of this potential energy function that's comprised of bonded terms, which we call bonds, angles, and dihedrals, and then the non-bonded terms. And so the idea here is that we're doing this numerical integration for millions of time steps. And the most computationally intensive part is, the contributions from these non-bonded terms. And the thing that makes MD challenging for doing parallel simulation is that your parallelism is really limited to each time step. The computational workflow of MD, we're initializing our particle positions and we're using these to calculate the forces. And then we're using those forces to update the positions. And we have this loop that we're in for millions of time steps. But the parallelism here comes from what we can do for this force calculation, right? But we have to calculate all these steps in sequence. Occasionally we have some output too, so the output might consist of these reduced quantities, that allow you to monitor your simulation, and also a snapshot of the trajectory of your simulation where you're writing the position coordinates out into a large trajectory file. And the force calculation, of course, comprises most of the work. And, then there's very little work associated with just the update of the positions. And the innovation that NAMD made in its development was not only the decomposition of the data for parallel computing, but also the compute objects as well. And so, it's if you've looked at all at parallel computing, it's kind of a basic idea that you want to decompose the work among, the hardware resources that you have. And so in this case, we're decomposing atoms into equal volume patches. And then we need to calculate the pairwise forces between atoms. Uh, and Most of this is the short range non-bonded contributions to the force. And so that would be between neighboring patches that we're computing. But the innovation in NAMD was to view these compute objects or the computation that's done as these independently schedulable compute objects that didn't necessarily have to be calculated using the same hardware resources that are, where you have the data for the computation located. And so, um, this actually gives us a lot of extra work that we can use to load balance the parallel calculation that we're doing, and so that allows us to get good scaling and maintain good performance as we're trying to scale large simulations across massively parallel architectures. Now, a couple of other things to keep in mind is that atoms move around. And so what you need to do is after every so many steps, you need to update the spatial decomposition. And so we call this migrating atoms. And this, atoms can't move too fast, or else we can't do this simulations in a liquid state that we're doing. And so this migrating of atoms takes place between adjacent patches. And uh, then we can also load balance the work when we're doing a parallel multi-node calculation. And so we do this by migrating the compute objects. And so the way GPUs were first introduced, and our history with GPU acceleration dates back to the advent of CUDA, which was in 2007. But, GPUs were a lot less capable back then. And we first introduced using this GPU offload approach and this ended up fitting in well with our multi-node simulation. So if you look at a computational diagram here, where we're thinking in terms of, the work that we're doing to get from one time step to the next time step, you know, well, and think of work as just flowing down in this diagram. So we're taking the patches that we've, integrated over, and then we need to calculate the forces for, those positions. And so this is a multicast communication that's done so that we can go ahead and compute the non-bonded and the bonded forces between these atoms. And at the same time, we're scheduling what looks like more of a point-to-point communication method in order to calculate the particle mesh AWOLD for the long-range contributions to the electrostatic forces. And so then we're computing forces for the next time step, and then we have something that looks sort of like a sum reduction, where we're taking these different components of the force and we're summing them back into the patches. And so the idea was that we needed to offload this force calculation to the GPU. And to do this effectively on a GPU, we need to aggregate positions together. And, when we started doing this, well, it makes sense to, focus on what, requires the most work to do. So those were the short range non-bonded calculation. But gradually over the years, we added the bonded computes and the scalable parts of the PME algorithm as well. Um, and the problem with this approach is that as GPUs got even more capable, um, what that meant is that the GPU offload approach we weren't keeping the GPU device busy. Uh, fully occupied, as we're trying to do this time stepping algorithm. And we had very fancy schemes for doing our force calculation on the GPU and then trying to stream back the partial results from the calculation so that patches could, as soon as possible, launch into the next step of the integration. And um, as GPUs got faster, we saw that we just weren't efficiently using the GPU as we would want to do. And so the whole idea behind GPU resident was then to uh, keep not just the data on the GPU, but do all the computational steps on the GPU. And the CPU really becomes something that has very little work associated with it. It's basically just managing the launching and of these GPU kernels, doing whatever data conversion that we need to do, going between the integration routines and the force calculation routines, summing the different force components together from the different parts of the force calculation that's being done. Uh, that was a schematic, but you can actually see this when you do a profiling of NAMD. And so when we look at the GPU offload mode running, we see here that the calculation in blue, and we see the communication that's done back and forth in red, and we see that for the GPU line on this, that we're really not keeping the GPU fully occupied, and so all the work that's being done on the CPU is causing a bottleneck to the calculation. And so then after the after moving to the GPU resident code mode of operation, we're actually keeping the GPU quite well occupied, and we have very little work left on the CPU. And so this gives you an idea of how we're using the hardware, between GPU offload mode and then the new GPU resident mode. And so what we wanted to do once we got things working well on a single GPU was to extend this GPU resident approach so that we could take advantage of tightly coupled architectures, because uh, that's a thing now. We have supercomputers now that are built with multiple GPUs in a node, and they've got a fast interconnect right between the GPUs in that node. And so, we want to be able to take advantage of this type of architecture as well. And so, in order to do this, we needed to take a similar approach, uh, except that we really needed a different data layout to be able to get good performance from the GPUs. And so we introduced a structure of arrays data layout. And uh, then what we needed to do, of course, was aggregate all of this compute and patch data to launch the integration force kernels, and divide these things between the GPUs. And we want to be able to exploit these tightly coupled GPUs, that are hooked together using NVLink or possibly PCI Express. And so uh, what we needed to do was uh, introduce something similar to what we have for the multi-node parallelism, um, where we basically have to again perform a position multicast into compute objects. Okay, and then we compute the forces on the GPUs, and then we perform a reduction back from the results of these compute objects back to the patches. And so to do this, the GPUs need a load store memory access between these different devices within every time step. And so, and the data sizes for these access are around 8 kilobytes per access. But once we had all of these pieces working together, we were able to get really good scaling for our GPU resident mode. So not only good performance, but really good scaling across uh, multiple GPUs. And so this just gives you an idea of, not only are we, running, you know, twice as fast or more than the GPU offload version is, but we're actually using the resources more efficiently too as we scale up. So in this example here, I'm just showing you a common benchmark, which is our million atom STMV system. This was the first virus that was ever simulated. It's the satellite tobacco mosaic virus, and chosen because it's actually pretty small for a virus. And so, and today it works really well as a benchmark system. Um, and so here we're showing a performance plot where I'm plotting nanoseconds per day versus the number of GPUs that are used. So a lot of recent work over the past 2 years has gone into improving the performance for smaller systems. And the biggest hurdle to performance was the fact that we needed to do this atom migration, where, atoms are moving around between patches as the integration's taking place. And so that was sort of, uh, the last remaining CPU bottleneck for just doing standard equilibrium simulations. We also exploited an AMD feature called two-way patch splitting, which basically takes your patch data structure and then just if you can slice it in any of the dimensions, but we like to slice along the Z dimension first. And so we can go ahead and double the number of patches just by slicing each of these patches that are created into two. And that creates more finer grained work units, and that allows us to have more work to schedule across the streaming multiprocessors of each GPU. And then another thing, finally, that we can use uh, once we get, you know, uh, small systems running at very high performance, we can actually co-schedule multiple jobs per GPU. And that's a way of, maximizing the overall throughput by keeping the GPU fully occupied for some ensemble of simulations that you're running. So, um, this was work just initially showing how much overhead it took to do the atom migration when it was still being done on the CPU. And our first version of GPU resident, the GPU or the time stepping parts that were done on the GPU were very fast. But then when we had to go and fall back to the CPU side to do this atom migration, oh, that was incredibly slow. And so, we saw early on that, we're really being held back by the fact that we need to do this atom migration. And, NAMD's default parameter at the time was 20 steps for every atom migration that you're doing. But the atom migration time was equal to 48 steps. And so, we were, you know, kind of in a quandary there that we decided to mitigate by uh, first extending the patch margins, and that allowed us to take more steps between each migration. And then we decided to monitor the atom movements so that we could perform migration only when needed. And then we needed a way of, for the migration parts to be able to use as many CPU cores as we could per device to decrease that cost of the migration. And so all of that taken together made CPU-based migration much more feasible. Then we were maybe only migrating every 400 to 500 time steps, and the migrations didn't cost nearly as much then. And so, but finally, we got to the point where we needed to actually like port the atom migration to the GPU. And so this required a lot of introducing a lot of extra data structures to the GPU that would store the topology data, and it would require, maintaining extra and managing extra buffer space so that we could basically receive atoms from the other GPUs. And then we needed to maintain a copy of the full atom data that's, stored in this in in an array of structures form rather than a structure of arrays form. And so really, it took a couple of, large development stages to get to this point, that included, refactoring the device buffers and then introducing the kernels for performing the migration. But it ended up benefiting all GPU resonant simulation, but especially smaller simulations where, you were really seeing the cost of that, having to do that migration on the host side rather than the device side. So our single GPU performance improvements, if you're comparing, uh, today's version of NAMD versus, a couple of years ago, we've really seen a lot of improvement where, for smaller systems like this DHFR, this is a standard AMBER benchmark, we can run that for over a microsecond a day now, which is, quite good. And we've seen dramatic improvement as we've been, able to add some of these optimizations to the code, and it especially impacts being able to do smaller systems really well on our GPU resident mode. So here are some benchmarks that I'll show, and I'll just show, that we can, scale really well on, larger benchmark systems. So here are the spike proteins for the COVID-19 spike studies that Romeo Morrow was doing. And we can see that, we're able to get really good efficiency scaling these on an 8-way DGX A100 platform. And of course, I showed you the STMV scaling earlier as well. And so we've made some real great advancements to our performance on this, going from, our NAMD 3 alpha releases to today's NAMD 3 beta releases. Now, if you look at something much smaller, like something, APOE1 is a standard benchmark for NAMD as well, but it's a little less than 100,000 atoms. And you see that, you have diminished scaling here for a system this size. And it's because you just don't have enough work to keep all 8 GPUs busy. In fact, you're topping out pretty early too. Yeah, I can't say I'd necessarily recommend this for even scaling across 2 GPUs. Although, 74% efficiency is respectable. But, by the time you get to 4 or 8 GPUs, you're really not using your hardware efficiently at all. And here's an extreme case. Okay, here's the tiny DHFR benchmark. Okay, you don't get any scaling on this anymore because it's just not enough work to scale beyond a single GPU. And so why am I showing you this? Well, I'm kind of showing you as to, what you can expect, how you might apply this hardware to your own systems. Um, but also, I want to introduce the idea that we can improve throughput for ensemble sampling. So, like I showed you on the previous slides, that, time sampling, of just a single smaller system offers limited parallelization, but when doing ensemble sampling, where you're running many independent simulations, uh, you can achieve, better statistics uh, and really reduce your overall computational cost by not just running one simulation per GPU, which might be a good approach, but possibly an even better approach is to use something called MPS, multi-process server, to run multiple simulations per GPU. And the idea is just to really keep all of the hardware on the GPUs busy, keep the streaming multiprocessors fully occupied. And so, although no single simulation will finish as fast as running one simulation per GPU, the aggregate nanoseconds per day that you can achieve over all of your simulations ends up being higher. Let me just show you some data to give evidence to support my point here. And so here we're running the little 24,000 atom benchmark system again, and we're seeing that if we're running across one simulation per GPU, we're getting around 874 nanoseconds per day. Here we're actually posting a lower time than I showed you before, but that's due to really measuring the full execution time, um, including the startup and the ending file I/O, all of it. And but if we move to two simulations per GPU, we're and four and then later eight, we're seeing we're actually getting much better uh, nanoseconds per GPU per day, and we're getting better aggregate nanoseconds per day sampling as well. And so um, this is a way that you can think about, using a GPU dense resource like this is to actually run multiple simulations per GPU. Here we had another example. This is actually published work here by Raphael Bernardi's lab. And so here we're showing a much larger system. It's 240,000 atoms, and we see that you can't just keep adding simulations per GPU. You'll get to the point where you're overloading the GPU to the extent that you're just not getting a performance gain anymore. You kind of flatten out on top. And so we found that the sweet spot for this with current versions of NAMD was two simulations per GPU. And so using MPS with NAMD, it's pretty easy to do. I'm showing you, just it's some simple environment changes that you need to make before you start launching your jobs, but then you can go ahead and launch jobs in the background, and they can use these GPUs together, for these different simulations. And so let me tell you some more about our advanced feature support for our GPU resident. And I'll be talking about these four methods real quick. First of all, today's NAMD 3, this is the first version of NAMD to have GPU accelerated FEP and TI. We're really pleased with the results. And it makes a huge difference in the performance that you used to be able to achieve in NAMD for doing free energy methods. So we support both GPU offload and GPU resident, but the GPU resident is much faster than GPU offload here, and we're seeing up to a 30-fold speed up over our what we used to be able to do if you go back to NAMD 2.14, and so we're yeah, doing really well here. This approach is also compatible with multi-GPU scaling if you decided to apply this to a system that's large enough. Um, Due to the expense of calculating the Langevin piston, we developed a Monte Carlo barostat. And the idea behind the barostat is that you're rescaling the periodic cell at fixed step intervals, and you might accept or reject this as a Monte Carlo move based on the new energy. Um, and so uh, it's ends up being a lot faster than the Langevin piston because we're avoiding the calculation of the virial tensor. And so the rescaling here is performed on the geometric centers of the molecules, and as a result, this is really only a feature that we're offering right now in our GPU resident mode to support, either multi-GPU or multi-node calculation. This would require quite a bit of extra communication, and we'd have to work out these messaging details. So this is a really nice approach for doing uh, you know NPT, constant pressure, constant temperature simulations if you're running on a single GPU. And so here I'm just showing you, this applied to our APOE1 benchmark, where you see that, if we have, a Monte Carlo frequency update of 100, that is getting almost the same level of performance of just running with Langevin alone. Uh, Another new thing that we now have available for our GPU resident code. I mean, it's been available since beta 4, but we had some bugs in the beta 4 and beta 5 releases. So, and we've improved performance now for the beta 6 release. And that is our Colvars module. And this is a highly requested feature from our users just due to the flexibility that Colvars permits in exploring um, various aspects of what you would be interested in simulating. And so Colvars is a modular framework for expressing and manipulating collective variables, and it can reduce the large number of degrees of freedom for your system down to its essentials. And so you can use this to monitor statistics, or you can apply biasing forces for enhanced sampling. That's really the normal use case is as an enhanced sampling technique. Um, it has a very flexible and deep interface, and the problem is that this library is a CPU-based library. It's not even developed by the NAMD team. It's developed by um, uh, people that are, you know, uh, involved with NAMD, but it's involved outside of NAMD, and so it this really is difficult because not only is the software itself designed in a way that is difficult to port to GPUs, but it's really not our code to port, and so um, it's really getting Colvars to be fully GPU resident is going to require co-development with the Colvars developers. Um, One thing we've already done is we've done some streamlining of the Atom data copying from device back to host for running the Colvars calculations. And but what we might need to do in the future is to port essential compute routines to the GPU. And so we're proud that it's a feature that's available. if you use it, expect that, it could slow down your simulation a little bit if it's a light collective variable that you're calculating, or if it's something that's a really heavy calculation, it could slow down your the performance of your simulation a lot to the point where you're really not getting any benefit from GPU resonant mode at all. So keep that in mind. Um, I'll skip over these two slides here where we're just showing that, on uh, uh, a when we're doing multiple time stepping and we have a PME step, we have enough work on the device side that we can, do a nice job overlapping what's being done with the host side calculation of the collective variables. But, if we're doing a non-PME step, we don't have as much work. And so then it turns out that we become bottlenecked by, the host side work for this example. Um, and so we have some initial results here that's just showing, that there is some loss in performance when we're, interfacing to culvars. But like I said, it really depends on the type of collective variable that you're running. Now, this was really to motivate uh, something that is called group position restraints. And this is essentially a very commonly used collective variable that we now have as a native implementation for our GPU resonant code path. And so the idea with this calculation is that you define a group of atoms, and then your position restraint ends up being the restraining of the centers of mass of between these two groups of atoms. And so um, So like I said, this is a native GPU resident implementation in NAMD of a commonly used collective variables case. And so just to show you an application, here is an example where we're restraining the head groups of a lipid bilayer. And so in this case, you know, you see that, this is just, the validation part that, the group position restraints is calculating what we would expect it to calculate. But what's, really impressive is the speed up, the performance speed up that we're getting with this versus trying to run, earlier versions of NAMD with uh, Culvar's implemented restraints instead. And so yeah, so this is, just a particular, collective variable here that we've implemented, but it's an important one. So, let's see. I'm going to skip over the Grace Hopper architecture slide right now. And instead, I want to talk about the idea that particle mesh AWOLD, the calculation for long-range electrostatics, actually introduces a scaling bottleneck for multi-GPU scaling. PME is important because it gives you a calculation of the full electrostatics, and but it relies on calculating 3D FFTs, and so 3D FFTs for molecular dynamics are problematical because they tend to be too small to parallelize effectively across multiple GPUs. And so for many codes, NAMD included, what we will do is assign PME to a single device. But uh, if you over-assign to one device, that causes load imbalance. And so this plot here, this performance plot, shows an extreme example where you see the PME evaluation stuck out here on this last device, and all the other devices are waiting for the PME evaluation to get done. That's bad because that means that those devices are idle and you're not getting, any performance out of those devices for, the way that we're doing our time stepping on this hardware. And so the key idea here is to make sure that the PME device is not overloaded. And we developed a way to do this in NAMD by exploiting task-based parallelism. So the idea is to use one device for PME, but then we'll reduce all of the other force calculation on that device by restricting the number of CPU cores assigned to that device. And so we're basically utilizing NAMD's existing patch and compute object distribution that we already had in place in NAMD, where it's trying to evenly distribute work across all the CPU cores that you tell NAMD that you're using up front. And so in this example here, I'm showing you profiling of running multiple time stepping. And you see that for the non PME step, or the step where you're not calculating the long range electrostatic forces, you're work starved on that one device. And I've just expanded the profiling here, so you're seeing an expanded version, but that's all work that's being done on a single device there that I have the red ring around. And so the first GPU is the PME device, and you are work starved on the non-PME step, but you're fully utilizing that device in the PME step, and you're doing it in a way that's not creating a bottleneck for the other GPUs. That's the really important thing. And so this is actually what is allowing us to get those good scaling across multiple GPUs that I showed you in previous plots. So I just expanded the second GPU here just so you can kind of understand the compute details, and all the remaining GPUs here on this 8-way GPU node are similar. And so we did some performance analysis work to try and determine some sort of, these aren't even heuristics at this point. This is just sort of like a guideline of how many CPU devices you might assign to the PME device versus the other devices. And so, if you're running on a single GPU device, it doesn't matter. That one GPU device calculates everything. But, it starts to matter how many cores you assign to that PME device when you have 2 or 4 or 8 GPUs. And so we sort of crunch the numbers here to, just determine, what the optimal work assignment for the PME device would be. And then that table presents it, right? So here I just want to conclude here by just showing you how to obtain and run GPU resident NAMD. And so you can go to the NAMD website and then go to the software download page where you'll want to choose version 3.0 beta 6, or later whenever we finish all the details involved with the final release. And the GPU resident mode is available to single process shared memory builds. And so, like I said earlier, the multi-core CUDA will be for single copy simulation. And so that's something that you would maybe run on your desktop. The Netlert's SMP CUDA build will be that will support multi-replica simulation where you have one copy per process. And you could run this in a way where you're running, just like a single simulation per GPU, or it could be a single simulation per node for a multi-GPU node if you have a large enough simulation to support scaling across multiple GPUs. Uh, the source code is available as a tarball on the site. You can also and so, that's the link there on the page to get access to our Git repository for NAMD. Um, the one config file parameter that you need to enable GPU resident mode is CUDA SOA integrate on. And I'll post some other information to the website as well that really presents guidelines that are good to follow whenever you're trying to run in GPU resident mode, and easy ways to do some initial benchmarking of your simulations so that you can determine for yourself that what you've set up is getting you the best performance you can get. Um, but just to give you an example of how the NAMD command line might look, um, here we're running plus P57, so we're running across 57 CPU cores, plus PME-PEs. Well, that's the number of cores that you're going to use for the PME calculation. And so, and then plus set CPU affinity, just make sure that you lock down those cores so that the OS isn't trying to migrate your job among different hardware cores. And then you plus devices, that gives it the list of GPU devices that you're running on. So this would be the type of command line that you might use for a DGX A100. That's an 8-way GPU box. And so the idea then, when you're using this plus PME PE's argument, is that plus P needs to indicate the total number of PEs. And so here we've set it to 7 devices times 8 PEs per device plus the PME PE's choice. And so this you know is is just the realization of that previous table that I showed, where what's the best option if you're running a PME across and scaling it across 8 GPUs. So I'll close with just some acknowledgments, and in particular, the programming team, not only includes myself, but the main contributors to the CUDA and HIP stuff are Eric Bohm, Haochuan Shin. We also collaborate with people from NVIDIA and from AMD and from Intel, and so I've just basically listed everybody here, and our grant information. Anyway, thanks very much for your attention.